All right, everyone. So today I'm going to be showing you how to use Fluent, ANSYS, and work with geometry in your wind tunnel. So here I have my wind tunnel pre-built from the last project that I worked on. I did make some changes, adding this surface as a curved surface just to help the overall pressure within the wind tunnel. And then I did start to just put some construction lines as far as where I'm building my flat plate to make the process a little bit easier. It seems to have frozen for the moment, but when it resumes, I'm going to zoom in and I'm going to start building my flat plate around this. So my dimensions that I am concerned about, I'm concerned about the blockage ratio. So my constraint is that the blockage ratio needs to be less than 10%. And since my diameter of my test section is 6 inches, my blockage ratio is going to be, or my blockage, my flat plate height is going to be 0.6 inches. So as I said, I started to do this. This is 0.3 inches, 0.3 inches. That way it's centered at the center of the wind tunnel. And then I'm going to make it 0.1 inches thick. So I'm going to come and diagram that, throw that in as a dimension. And then I'm also going to do it on the other side, just to be on the safe side. All right. And then I think the easiest way to do this would actually just be to insert a rectangle. Let's see if I can really pop out that point there. I want it over to, let's try that again real quick. I want this point here. Yeah. Not sure why it's popping that 0.9 every once in a while. But I know I can always go fix that later. Because what I can do is I can zoom in here and then do a coincident constraint. Pop that to that point. Awesome. So this is my flat plate. The next thing for us to do is to fill the surface. Make sure you're on select. Fill this, enable 3D. Yeah, that's how we do it. Enable 3D. And then I'm just going to come through. I like to go through and delete the construction lines just so they don't clutter up everything later. I think that's a personal preference, but I think it just makes my life a little easier. Okay. So as you can see, my flat plate is really tiny in the scheme of things, but we are good to go. So now we're going to go back to our workbench. We're going to come into mesh. Again, sometimes things just take a little bit to load since I am running so many processors at the same time, but it's honestly all good. Okay, so we want to be normal to our wind tunnel. And actually, when we're doing this one, the first thing that we're going to do is we're going to start with our selections. So we're doing some of the same stuff as last time. We're going to come over and create a name selection for our V inlet, or velocity inlet. We are going to select this and create a name selection for our P outlet or pressure outlet. And then we are going to select, making sure we're holding the control button down, all of our external surfaces. Right click and create that name selection one more time to make our wind tunnel wall. And then there's two other things that we're going to do for this one. We're going to zoom all the way in here. Select all of the surfaces of our flat plate. Create name selection. Flat plate. And now we can zoom out. And we are actually going to come back up here to, we're just going to go to faces and we're going to select this face. Create new name selection, and we're going to call this fluid. It just helps define that this is everything that's inside. And now we're going to come over. We're going to start working on our mesh. So I'm going to start by inserting I'm going to insert a method. This is my geometry, and the selection is going to be triangles because we love our triangles. We're going to come over to mesh. We are going to insert pretty sure. I know I do 2 inflations, so I can do those real quick. And then I think the rest of it's just a sizing. So I'm actually going to pull up my reference one real quick, just so I can pull up my reference values. Rather than having to do everything again from scratch, I'm going to pull up what I have been using. That way it's easier and I can show you guys what I have been working with. Okay. I'll just toggle back and forth. So my first inflation, under my geometry, I'm going to come over here and I'm going to zoom in a bit because I don't want the whole surface. I'm not totally sure why it's not letting me. Maybe if I have to come up and do edges again. Yeah. Okay. Make sure you're on edges for the toggle. You're going to double tap that top edge, control, and double tap your bottom edge. So now that all of your edges are selected, you're going to have, you should have 8 edges. Fluent definitely has a learning curve. Not my favorite software to work with. I also don't know why it's doing this at this moment, but it's okay because we're going to get through this together. We'll just start over, try it again. If you're watching this and you find that you're getting really frustrated with Fluent, just know you are not alone, my friend. It's a really tedious process that is not the most fun. Let's come back, try those edges. There we go. I was able to toggle it from here. So that's why name selections are also really important. Toggled my wall there. Or maybe not. Nope, I didn't toggle my wall there. Tried that again. Okay. That's why. Let's try doing it in boundary. Let me toggle back to this and see if there's something I'm missing. Okay, let's try doing it this way. So geometry, I'm going to click on that and apply. Now it should let me click on my boundary. That's where you're going to double click. Troubleshooting and process. It's all good. Honestly, it happens. We're going to toggle that to first layer thickness. And then this, you just really got to play around and see what works with you. So the value that I found really works. We're going to toggle over to show you. I was using 2 times 10 to the negative 3 inches. I'll show you with a different value just so you see a difference in there. So I'll do, we'll do that and see what kind of difference that makes. I'm gonna do 15 for the maximum layers, and then growth rate, I'll do 1.02. Again, it's just kind of playing around with these numbers to see what really works and what makes a difference and what gets that boundary defined how you want it to be defined. So now that this inflation's done, we're gonna come and do another inflation. Again, we're gonna select our geometry first to be able to come in and scroll all the way in and select our flat plate geometry. This just really helps us see and define the boundary layer of what we're working with. Because without this, we wouldn't be able to get the really good details. So I think that's what I put for the last time. Might have been one more 0, but it should be okay. I'm gonna give it 20 maximum layers on this one, and I'm gonna leave the growth rate alone. And then the last thing that I did was a sizing. 99% sure. I'm gonna toggle back just to double check myself on that. Okay. Yeah. So I did do a sizing. The sizing again was also on these 4 lovely surfaces here, just to really pop out the boundary layer conditions. So it's definitely going to take a while to mesh, but the smaller you make the element, the more defined it's going to be. And it does have 4 edges, so I'm not sure why it's not showing the bubble on all 4. I'm going to also shrink the growth rate down to just nearly 1, just so you can really see it. And then we should be good to generate that mesh. It's going to take a while just because this was a very super defined mesh, and it did have a lot of moving pieces, but this allows us to really zoom in and get the details of our wind tunnel. I might have to go back and rechange this because this, to my knowledge, should not be showing like that, but we'll let it do its thing and then we'll see what we have to do. I'm gonna also come over and just exit out of this last one to see if I can free up some processing power. One of the things that I really do like about Fluent is that everything is saved regardless of whether or not it's open. So you don't have to worry about saving a project until you are done with it. It's probably a good practice to save it sooner. But should you accidentally close out of something, it's not lost forever. There's a local copy saved through the program being open. Hopefully, since it's taking a while, we're going to get a really nice and defined mesh. What my hope is. Really is taking a while on this one. It hasn't taken this long before. I know that I've done everything correctly. Ooh, let me see if I can get out of some of this and free up some more processing power. Get out of this as well. That should really make a difference. If it doesn't finish shortly, I will go back through and see if there's anything I need to reevaluate. Definitely struggling. Let's just try this again. Let's get that to stop. See what happened. I'm pretty sure something is too tiny. I'm gonna change this back up to 1.2 and see if that makes a difference. All right, so I'm pretty sure my computer has just decided that it's done for the day. It doesn't want to do anymore. So what I'm gonna do is I'm gonna stop this again and I'm gonna show you what I have for the completed part of it. It's gonna be a little unconventional, but I think it's going to be the best way to move forward with this video at the current time. I'll just break down really how I set this up and where things are at. I use the exact same process that I just showed you and demonstrated, and I'll regenerate the mesh on this one as well and see if it's just something going on. I do think my graphics card just kicked in. So, like I demonstrated in the last one, this is what I set up for my edge sizing, all triangles, and the two inflations. The two inflations really just let you zoom in on the edges and give you some really nice definitions so you can see the boundary layer. Let me get that. We'll do it over here, I guess. I've been spending a lot of time in a different software that has definitely messed up how I work with Fluent. Let me see what I can do. It's not zooming in quite like I'd like, but if you can kind of see on the edges, it just goes from like straight to flat. It really gives a well-defined boundary layer. I'm gonna refix this and zoom back out, and we'll keep moving along here. So now that I've got this, I would go back to this, and this would have the lightning bolt on it, and I'd come in and I would right click and update. I'm just gonna push an update anyway in case something has changed. Then I would move into my setup. For this, I'm using double precision and I allocated 4 solver processes. I'm pretty sure that my computer has enough to handle that, so I'm just gonna go ahead with this. It really has been one of those days, it's almost spring break. My computer is just as tired as I am. So now that we're here on the mesh, we see that our inlet and our outlet are defined, which is awesome. That's what we want. We're gonna come up here and we're going to make sure that we have our energy on. We are also going to check that our material is an air. There's one other thing, our viscous. So I just switched it over to K epsilon. I like working with K epsilon. I think it's really a personal preference. Depending on your project, what you got working on here. I'll be working in K epsilon for this one. We're gonna go and we're gonna start defining our boundary layers. So we've got our fluid, which is inside. We're good to go there. Our boundary conditions, our V inlet is what we're most concerned about. So we're gonna come in here, not rename it, and we're gonna check what our velocity magnitude is. So for this case, we're working with 50 hertz, which means that our test section target velocity should be around 12.07. And then in order to do so, we use our height ratio of 6 inches to 22 inches to backtrack and get this as our inlet velocity. It's just something that you play around with again to try and find and match the conditions as much as possible. So I found this to be a really good match in my scenario. After you hit apply, you're going to close. We're also going to check our interior fluid. There's nothing we can do with that. That's just our fluid. Our outlet. So our gauge pressure is 0, which means that our inlet should be the exact same as our outlet. Ideally, we want to correct for this, but we are not going to be doing that here. Close. And then we see we've got 2 walls defined, our flat plate and our wind tunnel wall. Both of them are stationary walls. There's no slip condition, and we don't have any specialized roughness or anything going on. So we're going to apply and then close on those. The other thing we're going to need to do is set up a report definition. So I'm going to delete the one that I have here, and I'll set it up again just so we can walk through that. So we're going to need a new report definition of drag. So we're going to come over and name this drag plot or drag report. It's going to be pulling the drag force, not the drag coefficient, because the drag coefficient can sometimes pull it from the wrong location, whereas the drag force is just generic through the wind tunnel. We're going to pull it from our flat plate, and there's no other thing that we need to do with that. I think we also need to toggle our plot just so we can see it come out. Then we'll hit OK. Then we're going to toggle drag report and close. We're going to come over and we're going to initialize everything we set up. It's really your choice on whether to do hybrid or standard. I'm going to stick with hybrid, and I do 25 iterations just to make sure that it does converge. So I think at this point it has met the tolerance that I have predetermined, but I'm just going to let it run all the way out that way I can get as precise as possible. Now I'm going to come in, I'm going to run the calculation. I run it to 200 iterations just to, again, make sure it converges. I'm going to let it run all the way through rather than stopping it sooner. Just, again, to reach as converge as possible. And then I'm going to calculate. So it definitely seems like it's going to be taking a hot second to do what it needs to do. So we're just going to sit back and wait. So it looks like we're really starting to see some forget what it's called, but when it's really starting to converge on a value, which is really good to see. Let's check some of our other plots. So these two are doing the same thing. And then we're seeing these are starting to flatline out as well. which is good. We're just gonna let it finish. That way we get as precise as possible. It's really interesting to see the drag at the beginning jump like this. I've run this before where it's gone up and it's also gone just as far down. It's just really how your computer is interpreting what's coming through and what it decides to do during the trial that it's running. Looking good. It's good to see. This one's becoming really, really solid, which is nice. This is definitely a really long video. Feel free to skip through a lot of this, a lot of the sitting and watching, which I'm sure you probably have already. This is more just the procedural side of things, watching the data become data. The fun part. Only 25 iterations left. We're almost there. Woo! He's almost done. Okay. So let's start by looking at the drag. We're going to come down here to reports. We're going to click on forces on a flat plate, and we are just going to print it to the screen. This is our report of the forces. It's really what we expected. Actually all of the drag comes from this pressure drag. What's really interesting to see is we have this minuscule amount of negative viscous drag. That's also because like it is a blunt body. So this is really what we would be expecting to see from a blunt body versus a streamlined body. And then that's our total drag. So it's just take a screenshot, write those down, get them into a file. That way you can recalculate this coefficient because this is not the correct coefficient. So you're going to use your non-dimensionalized coefficient equation to use this and solve for it. But back to the rest of the fun data. We're going to go into graphs. I'm not going to spend too much time rebuilding these just because these are the exact same plots that we pulled for the last project. So our velocity plot, velocity magnitude, of course, and we're just doing it on our fluid this time to really see what's going on. So I'm going to save display this. We'll zoom in here. And then as you can see, this is about what we'd be expecting. You've got these, almost like these stagnation points right here, where you've got this really good streak of flow happening. This is the velocity. You can see we've got this region here. All this is zero velocity, but we've got a little bit of, just a little bit, but a little bit of velocity in here. Our free stream velocity, all this light orangish reddish stuff, is right in between the 11 and the 13. So just around 12 meters per second. And then we actually have an increase of velocity in some of these regions above what our free stream velocity is. So that's interesting to see. And then we're going to come over here and pull the static pressure. It's going to look pretty similar, but actually just the inverse of it. So save compute, we're also doing it on our interior fluid. We also have points right here that are very important. We got our free stream pressure, be about what we expected. Very wide range, and we've got a lower or a negative pressure on this side of the flat plate. And then the other new plot is a streamline plot. So I will rebuild that one to show you. So you're going to come into streamline. We're going to come down here and do a velocity magnitude. We're going to lower this down just because we don't need it to be so high. We're going to do a 4.2 just so we can get the good detail. Then we're going to do it, I believe, on the flat plate. Might be the fluid though. No, it's definitely the fluid. We're going to do another fluid. We're getting through it, everybody. Got this. Okay. Save display. So as you can see, it was very similar to our velocity contour, but what really differs is you can see these vortices forming in here. So the flow is definitely in these two spots, making these loops. You really get to see what's happening in these regions where you've got the stall. And then you also get to see some adverse flow here. So it really does get to show you that good detail. And then that is it for the scope of this project. It's just the two streamlines. Remember your drag forces and how to calculate that. And then you are good to go. I hope this helps. Bye.